Hello everyone. As I said in our previous video, we have laid out all the foundations and learned completely the concept of OFDM-SPM. So only one thing left now. How will it perform though? Let's find out. So welcome to our third video, which is simulation results. What does all that mean though? So first of all, I'll just give you a small brief overview of the software we used and the nature of the simulations that we're going to do. These simulations were done in MATLAB, and they are Monte Carlo simulations. This means that they're probabilistic, since the noise and channel response parameters are modeled probabilistically and are continuously changing. The metrics which these simulations test the OFDM-SPM on are bit error rate and throughput, where bit error rate, or BER, represents the ratio of bits received in error to all received bits. It's a metric which determines how erroneous or reliable a telecommunications system is. So smaller bit error rate is better, basically. You don't want too many errors. And as for throughput, which is bits per second per subcarrier, on the other hand, it represents how many bits are transmitted and received correctly per certain measure of bandwidth, which in our case is one subcarrier. So coming to the simulation parameters, you'll find in the table on the right all the simulation parameters used. As we mentioned before, the modulation scheme we're pairing with OFDM-SPM is QPSK. And the results of the simulation were actually done for both an additive white Gaussian noise channel and a Rayleigh fading channel, as fading channels mimic wireless channels more accurately. So coming to the MATLAB code. The MATLAB code we use to generate the simulation results found in the paper can actually be purchased through the link. You'll find it in the video description. Alternatively, you can just go to researcherstore.com and simply search for simulations of OFDM-SPM with QPSK modulation. You can purchase it from there. Take a look at the code. It's relatively simple. It's well documented, and you can replicate the results in our paper, but more importantly, you can build on top of it. We need to keep the research going. So let's come to the simulation results. Well, we simulated 4 cases for OFDM-SPM, which are firstly OFDM-SPM with power saving, and then OFDM-SPM with non-optimized power reallocation. So this means that the power was reallocated, the saved power was reallocated, just not in an optimal manner, just to show you how important it is to determine the optimum L and H values. And then after that, we simulated OFDM-SPM with optimized power reallocation. And last but not least, we have OFDM-SPM with QPSK in comparison with conventional OFDM with 16 QAM. Since both of them achieved the exact same data rate, we said, well, why not compare them? Let's see how OFDM-SPM compares. And the results were quite striking, actually, in a good way. So first we come to OFDM-SPM with power saving, looking at the BAR. So as you can see, the optimal values were found to be L equals 0.4213 and H equals 1.35. This was the values were found according to the following constraint. And well, as you can see, the average simulated BER of OFDM-SPM in a Rayleigh fading channel is the one in blue. Whereas the one of conventional OFDM is the one in green. And well, as we said, smaller BER is better. So from that, you can obviously see that there's a big degradation in BER, that conventional OFDM in terms of BER outperforms OFDM-SPM in a Rayleigh fading channel. Similarly, the same thing can be said about in an AWGN channel. As you can see, the green line has much lower BER values. When using the power saving policy, there is some degradation in the BER. However, the gain in throughput is also equally good. So something else that I would like to point out is we also simulated the power errors separately, which are shown in black for a Rayleigh fading channel, and which are showed and the QPSK errors are showed in red over here. So so you can get a complete picture of the simulation results. So looking at the throughput, as you can see, the average throughput of OFDM-SPM in a relay channel is the blue line right here. And conventional OFDM, on the other hand, is this green one, the green dotted one over here. So as you can see, even from very low values of SNR, signal to noise ratio, you can see that the throughput of OFDM-SPM is much better than that of conventional OFDM. And the same thing applies to an AWGN channel. As you can see, as the SNR gets higher, OFDM-SPM, its throughput saturates at a value of 4, whereas conventional OFDM saturates at a value of 2, which is literally double the throughput. So that's a great performance. So we come to our second case, which is non-optimized power reallocation. So first of all, what we do is we look at the BER. In this case, we assume the following values for L and H. As we said, this is non-optimized. So we gave L a value of 1 and H a value of 1.732, according to the following constraint. This case shows that there is still some gain, as you'll see much more clearly in the throughput. However, if you look, what happened over here was the average performance, the average BER performance of OFDM-SPM is much worse than conventional OFDM, as you can see. However, looking at it from another point of view, however, the BER performance of QPSK when using OFDM-SPM, however, was actually better than that of conventional OFDM. So in conventional OFDM, you only have one stream of data, which is with this performance. Whereas in this case, in OFDM-SPM, you have two streams of data with two different performances. So you have the QPSK symbol one, which is actually better than the conventional OFDM one. And you have the power one, which isn't performing that well, but nevertheless, it's still extra. So in the long run, you're actually gaining. And the only reason that this average looks so bad is because, well, it's an average. And averaging two quantities when one of them is large and the other is low, it just lifts it up with it. And the same thing can be said about the AWGN channel. As you can see, the QPSK, the OFDM-SPM QPSK bit error rate is actually better than that of conventional OFDM. Whereas the one for the receiving the power bits does not perform very well. However, as was said again, this can simply be seen as an extra. Furthermore, this can be used for different cases. For example, imagine that you have two different users and two of them need two different requirements. One of them doesn't really need a very high bit error rate. You can just give him this data stream and give this one to the other user who requires a higher bit error rate, a better bit error rate, pardon. Now coming to the throughput, where everything really shows a lot more clear, you can see that the throughput of OFDM-SPM in a conventional, in a relay fading channel, much outperforms that of a conventional OFDM. And the same can be said for an AWGN channel as well, as you can see, and over here. And just as the BER showed, the performance of OFDM-SPM through QPSK symbol modulation is actually better than conventional OFDM with QPSK, as the throughput here, the red one, is higher than the green one in an AWGN channel, and the same applies for a relay fading channel. So what if we optimize the power reallocation? Let's see how the performance is then. Well, when we optimize the power reallocation, we found the values of L and H to be as follows. L equals 0.5668 and H equals 1.918, according to the constraint below. So as you can see, although there is still some degradation in BER when comparing the blue curve with the circles in it, which is the average performance of OFDM-SPM, it still lags conventional OFDM slightly in terms of BER actually. And this can be said for both a relay fading channel and an AWGN channel, as you'll see over here. However, another thing that we'll notice is that if you look at this purple curve right here, that's conventional OFDM with 16 QAM. And 16 QAM achieves a data rate identical to OFDM-SPM with QPSK. And in this case, even though OFDM-SPM is using half the power used by conventional OFDM with 16 QAM, it's actually outperforming it in terms of BER, even though it's achieving the same data rate. Now, when coming to throughput, actually, you'll notice pretty much the same thing. You'll notice that OFDM-SPM, on average, outperforms conventional OFDM much better when comparing both schemes with QPSK. And it saturates at a doubling at the power rate. And the performance of conventional OFDM with 16 QAM is almost identical to OFDM-SPM with QPSK symbol modulation. Even though, as I mentioned, conventional OFDM with 16 QAM is still using twice the power that OFDM-SPM is using. So in that case, well, what happens if we make the power, if we reallocate the power that OFDM-SPM is saving in this case? What if we make OFDM-SPM with QPSK use the exact same amount of power that conventional OFDM with 16 QAM is using? Well, the results turn out as follows. So we use the equation below to determine the optimum L and H values, which are 0.8426 and H equals 2.7. When you look at the results, you'll find that the average BER of OFDM-SPM is better than that of conventional OFDM with 16 QAM by approximately 2.5 to 3 dB, which is quite a lot. Furthermore, this gives the users of OFDM-SPM flexibility, as they can save power, just as they did in the previous cases. They can save the power, half of it, and achieve the same results achievable by conventional OFDM with 16 QAM, or use the power and obtain more reliability and performance. It all depends on what you need. And, well, this can be pretty much seen for both the cases of AWGN, which is additive white Gaussian noise channel, and in a relay fading channel as well. So coming to the throughput, you'll see right here that the throughput is OFDM-SPM still provides a better throughput, as you can see, even though both of them saturate, as the SNR gets larger, both of them saturate at a value of 4. However, initially, OFDM-SPM still provides better performance both in a relay fading channel and in an AWGN channel. So what do these results tell us? Well, as we saw, OFDM-SPM is able to achieve a doubling of the throughput in all of its cases as the SNR gets larger, at the expense of some degradation in the BER. However, when comparing OFDM-SPM with QPSK with conventional OFDM with 16 QAM, OFDM-SPM even displayed a better BER performance. And it can also be said that BER degradation, when compared to the gain in throughput that you get, is actually an acceptable trade-off that we're willing to put up with. The results show also that unlike other schemes which add a third dimension to modulate data such as OFDM-IM, OFDM-SNM, OFDM-SPM maintains the gain in data rate and spectral efficiency even when matched with a higher order modulation scheme such as QPSK, which uses both the in-phase and quadrature of carriers. In other schemes, however, the spectral gain was limited to lower order modulation schemes. This is a unique characteristic of OFDM-SPM and could prove to be, with further research, its most important characteristic actually, as it lays ground for scaling this system and thus increasing its number of applications and use cases. OFDM-SPM gives the user much flexibility as it offers in different power allocation policies and can reduce complexity according to the application needed. Due to all of these advantages, we can say that OFDM-SPM introduces itself as a candidate for future 5G and 6G communication technologies. So how does OFDM-SPM compare to other schemes, though, which have been previously introduced? As we said, OFDM-SPM has displayed the following advantages over its counterparts. It achieves a great gain in terms of spectral efficiency and data rate, although there is some degradation of VAR in some cases. However, the gain is much larger, and OFDM-SPM displays a gain in terms of VAR when compared to conventional OFDM with 16 QAM, which is approximately 2.5 to 3 dB. OFDM-SPM does not lead to any kind of error propagation, unlike some other schemes. The results show promise in scalability, even though this needs some more research, such as pairing OFDM with even higher order modulation schemes and how it would fare. However, the results thus far are promising. It also adds minor computational complexity when compared to what other schemes have added. Even though OFDM-SPM and some other schemes might be in the same, their receiver complexities might be in the same order of complexities. However, when we look at it from the point of view of floating point operations, OFDM-SPM is far less complex. And furthermore, OFDM-SPM adds flexibility, as we said. And this is important as it allows it to introduce itself as a solution for many different applications. And that's exactly what 6G and IoT needs. So that was everything for this video. As you can see, the simulation results are rather promising. In the next video, we're going to wrap everything up with a small conclusion and look at our future work, what future research could be done with regards to OFDM-SPM. And by that, we will conclude our short video series on OFDM-SPM. I'll see you in the next video and see you soon. Stay tuned.